In the interest of eventually, quickly, hopefully getting to string theory, there was one other motivating factor that you didn't mention when I initially asked you why you got into string theory, because you were interested in reconciling quantum theory and gravity. That I'm curious about because I know it's a motivation for a lot of other people who work in string theory. One person that comes to mind is Linda. I'm not sure if it's Linda or Lindy here at Stanford, but that is fine tuning, and I didn't pick it up in on looking at any of your papers. But how do you think of the apparent fine tuning of the universe? Do any particular aspects of this stand out for you, and is it at all a motivation for your pursuit of string theory, or you don't really think about it?
Um, Fine tuning. Which fine tuning are you talking about? The cosmological constant or the?
Not just the cosmological constant, but not just the cosmological constant, but why the forces have the strength that they have, the particular assortment of subatomic particles we have, and if any of these things were different, uh, some are more sensitive than others, life wouldn't arise. So there is a question of why things are the way they are, why we find ourselves in a universe that supports life like us.
Yeah. So I guess this is this is an old problem. Um, uh, I think Dirac called it the large numbers problem. Ratios of y is, if we take the ratio of the Planck mass, which is the mass of a black hole whose Schwarzschild radius equals its Compton wavelength, to which it's sort of a basic mass scale in physics, to the mass of a proton. That's a huge number. It's like 10 to the 20 or something. And then we can take the ratio of that to the cosmological scale, another huge number. And so when you have these numbers that are so big, if you take a piece of paper and write down the laws of physics as we understand them, they're going to be ratios of numbers which are 10 to the 20 or more. In case of a cosmological constant, even more. And that, that demands an explanation. We'd like to know why. Why is the ratio 10 to the 20 not 10 to the 15, let alone 5? If you throw a couple, if you grab some, what's a good example? Most numbers would ordinarily be 1. If you balance your checkbook, if you write checks and you spend money at the end of the month, the difference between what you earned and what you spent is not going to be hopefully it's a number of order 10 to the 20. It might be 1. It might be a factor of 10. It might be a factor of 100, maybe even a factor of 1,000. But it's not going to be a factor of a trillion. And if it is, you'd say, wait, I think I made a mistake in my computer program or however I calculated this. But we're pretty sure there isn't a mistake, that these numbers differ by some huge amount. And we'd like to explain that. Now, there's been a lot of brilliant work coming up with explanations why it would be normal and expected for this to be true. Some of it involves supersymmetry. Some of it involves the anthropic principle. And I think it's fair to say that despite the brilliant, first of all, the huge amount of work far more work has gone into this question than into the problem of quantum gravity, far more. And so, and largely because it has to do with things that we measure, and we might think there could be some prediction or something coming out of it. I think it's fair to say that the reward to effort ratio in this enterprise has been extremely low. That despite the clever ideas and approaches and so on and so forth, we just don't understand it. If I had an idea to explain, so that's why this is why science is not a science, science is an art. If I had an idea how to explain why the cosmological constant was so small, I'd stop everything I was doing and I'd cut off this phone call and I would go and work on it. I don't have an idea. And my own view, though lots of people are working on it, nothing looks very promising to me. And of course I could be wrong. I'm just guessing. I don't think you alluded to the anthropic principle. No, it could be right. It's not a logically inconsistent thing, but it not only has to be right, you have to be able to do something with it. You have to be able to make a prediction. It's not enough to explain something you've already measured. I'm not saying what's right and wrong in science, but as a I would say incontestable sociological fact. If you come up with a theory that explains something that has already been measured, that's not enough. To confirm the theory, you have to make a prediction, tell somebody to go to measure it, and then they have to come back with something that agrees with you. Some famous example of this was the precession of Mercury's perihelion, which was measured by Leverrier in 1859 to be off from the Newtonian prediction by 1 part in 100 million. And, the planetary orbit, Newton was almost exactly right. He was off by 1 part in 100 million, right? And you got to admire these guys. Okay, so that sat there, and somebody said, okay, it's only 1 part in 100 million. There's probably some dark matter, which, by the way, is now used to explain everything that we don't understand. There's probably some dark matter.
That or aliens.
That or aliens, right. There's probably some dark matter floating around out there that we don't know about, and it's moving, it's affecting Mercury. That's the 1 part in 100 million effect. And they convinced themselves that this dark matter theory was correct. So when Einstein came along and gave the real explanation, nobody was interested. They're like, are you kidding me? You're telling me that space-time is curved and your evidence is that Mercury's perihelion is off by 1 part in 100 million? But then they listened when he said, yeah, that's what I'm saying. And if you look at the next solar eclipse, you watch the star go by, its position is going to move in the sky. And Newton would have told you it's going to move this much, and I'm saying it's going to move twice as much. And that turned out to work. So that was a prediction, experimental prediction. So the anthropic principle, maybe it's explained, because if you explain something that you already know, that's already been measured, people are suspicious that you've cooked the books. That you went out and searched for it. You're not finding something new. That you went out and cooked the books. You cooked the books. So Einstein knew he didn't cook the books, but he wasn't able to convince anybody else that he had until he made a prediction. So I don't see the anthropic arguments leading to a robust, measurable prediction that will persuade the. So I don't think it's going to go that far. I don't really know whether I think it's right or wrong. They tried to use the anthropic principle to explain the periodic table. That if the elements didn't have just the right weights, you wouldn't be able to have life, and so on and so forth. And this was the reason for the different atomic weights. And then, of course, you had the Bohr atom, nobody was interested in the anthropic principle anymore. So I think it's an important problem. It's not what I don't want to dismiss the problem. Every once in a while, I think about it to see if something I've learned in the last 5 years triggers some approach to it, but I don't sit there and bang my head against it. I bang my head against the black hole problem because that one keeps it moves when you bang it, and it seems like we keep learning more, and I have a feeling that we're making progress on it. And I think that would be the one thing that everybody who works on it would agree on, that we're making progress. They wouldn't agree on what the progress was, but they would agree on a few things. They would agree on a few things, but they would disagree on.